So, to complete chapter 1, let's talk about, what the big picture is and why we have been talking about everything we've been talking about. So, we've talked about models, and models have parameters. The Gaussian has two parameters, the mean and the variance. The exponential has one parameter, the scale parameter. But later on, we'll be talking about complicated models that may have 10,000 parameters, all of which we wish to learn from the data. And presumably, the models with their parameters are what generate the measurements that we can also call the data. And sort of the philosophical thought process of going from models that have parameters to the data itself is called kind of a generative model, because your parameters in your model are what generate the data. And the whole point behind this class and what we're doing is to go from the data to the model, or more specifically, the model parameters. And this is called inverse modeling. So oftentimes, sort of in classical education, chemistry and physics and, other disciplines in the sciences, and engineering for that matter, we start off with models, we generate data, and then we compare that we generate sort of predictions, and we compare those predictions to the data. Here, the attitude of this class is completely different. We're doing data modeling. We're starting from the data, and from the data itself, trying to sort of infer the cause, or in this particular case, the numerical values for the parameters. Let's talk about a very simple approach to this problem. And that very simple approach is by likelihood-based methods. But first, let's talk about what is a likelihood. We'll turn to likelihoods in a lot more detail by the time we get to chapter 3. But for now, let's talk about what likelihoods are. We have some probability, W1 to n. That's the probability of the observations given parameters. So my likelihood is expressed as a conditional probability. So let me just write this out in words. So it's the probability density, I should say more precisely, of the data, W1 to n, given the model and its parameters, more precisely, with values theta 1 to k. So let's try to answer a very simple question. What is the probability of W1? W1 could be, for example, outcome of heads in the case of a coin flip. So this is an example. Coin flips have one parameter, the probability of heads. And I know that the probability of tails is 1 minus the probability of heads, which is why I'm saying it's one parameter. So what is the probability of heads given a pi of 0? That's weird. That's saying that the coin will never flip heads. Well, what is the probability of heads given that the coin never flip heads? And the answer to that is 0. Okay. What is the probability of flipping heads when pi is 1/3? Well, then that's going to be straightforward. It's going to be 1/3. Okay. What is the probability, now let's make it a little bit more complicated, of flipping heads, heads, tails, given that the probability of heads is 1/3? Now this becomes a more interesting problem. This will be the probability of heads, so that's 1/3 times 1/3 times 1 minus 1/3, which is 2/3. So if I do my math correctly, that's 2/27. That's the probability of heads, heads, tails of that sequence, given that the probability of heads taken by itself is 1/3. Now, these are easy examples that I can do by hand here, but Later on, we'll be doing much more complicated examples where you can't just guess these things. Now, notice how the fact that I had specified the numerical value here changes my answer on the right-hand side, right? So, how can I use likelihoods in order to estimate pi? That's really my question, right? So, I'm not interested, or I may be interested, but for the moment, I'm not really interested in calculating what the probability of a sequence is. I'm given a sequence, and I want to learn, so that's the data, and I want to learn pi, the model parameter. That's my goal. How am I going to do that? Well, I will say what value of pi makes the sequence of observations or measurements or data observations W1 to n most likely. Now remember, this object here is called a likelihood. It's the likelihood of the data. So what value of pi makes the sequence of observations W1 to n the most likely? I'm going to write something down here, and I'm going to explain what I'm doing in just a second. But what I'm basically saying here is if you take your likelihood and you maximize it with respect to pi, you obtain an estimate. That's what the hat means. You obtain an estimate for pi, which makes the sequence you have observed the most probable. Okay? This is, we can try to guess what pi makes this sequence more probable. Suppose I had collected data for 3 coin flips, heads, heads, tails. What is the most probable value of pi to explain this result? Well, it should be 2/3. How do I know that? Well, let me write down the likelihood. The likelihood is going to be equal to pi times 1 minus pi, right? Because I've observed heads, heads, then tails. Okay, let me simplify that right away to pi squared times 1 minus pi. Now, what value for pi makes this likelihood the largest? Let's think of, something silly for now. Is it pi is equal to 0? No. If pi is equal to 0, then the likelihood is 0. Why? Well, because we have observed a heads. We have observed a tails. So we know that pi can't possibly be 0 because we've observed heads twice. Okay, well, let me make another guess. What if pi is equal to 1? Same thing. Why? Well, because we have observed a tails. So we know that pi can't be equal to 1. So somewhere between 0 and 1 is the correct value of pi. Let me plot this likelihood. Let me plot the simple function and see what it looks like. So I'm going to plot pi squared times 1 minus pi from 0 to 1. And what I should get if I plot it will be something that looks a little bit like this. And this here, I should say this here is going to be, and I'm plotting it versus pi. This here is the value of pi for which this number is at its maximum. And the value of pi for which this function is at its maximum, or I should say pi hat, is 2/3. So if I maximize with respect to pi, pi squared times 1 minus pi I better get a pi hat which is equal to 2/3, because I've seen heads twice and I've seen tails once. Well, that looks like a very complicated way of estimating the probability of heads and the probability of tails. Of course, the reason we're doing it in this complicated way is because this complicated way generalizes, while, sort of trying to guess things by counting how many of certain outcomes I have is not necessarily a generalizable strategy. So, for example, I'd like to be able to estimate rates of reproduction of bacteria, or I'd like to be able to estimate certain amount of time spent in particular states. This should be pi hat. Then what I would do is I would write down my likelihood for that problem given parameters, and then I would try to maximize this in general with respect to these parameters in order to be able to obtain parameter estimates that optimize the probability of the data as I have observed it. That fundamentally is the inverse problem. Inverse modeling in general is hard. So it's easier to come up with the causes, make predictions, and compare those to data. Taking the data and trying to infer the causes is hard. And you can ask the question, why is it hard? Well, the problem may not have a solution. Especially if you're starting with the wrong model, you'll get nonsensical results. The solution may not be unique. This is all typical of inverse modeling. So there could potentially be many different solutions that explain your data all equally well, right? Maybe this likelihood here, if I were to plot it versus the theta, has kind of like a ridge of potential solution. And finally, the solution, and this is one of the toughest ones, may vary dramatically with the supplied data. So I can gather a couple of different data points and try to estimate sort of a division time for cells. And my data points are 32 minutes, 31 minute, 29 minutes, and suddenly there's another cell whose division time was 120 minutes, and suddenly my estimate for sort of a replication time is dramatically impacted by that one data point. So the solution, or my estimates for theta, may vary dramatically with the supplied data. That generally is not the case for forward modeling. The solution may not be unique. Again, that's often not the case for forward modeling, but it's almost universally the case for inverse modeling. And the problem actually may not even have a solution. So this is kind of what makes inverse modeling so challenging, and yet it's so important, which is why we have to address all of these separate points independently. So our goal is now basically to try to address the inverse problem across multiple paradigms. And a very important paradigm we will be dealing with is dynamical problems. Problems that have time, problems that have evolution and dynamics that we now turn to.